This is Chapter 3 of my lecture outline series, and is chemical equations. Everybody should know what a chemical equation is from a context standpoint. If I said chemical equation, you know it's a symbolic representation of a chemical process or chemical reaction and so forth. We know that it consists of one side or the other reactants, yield products. Nothing new here. Be sure you note that you can find equations that will have arrows going both ways. If you have arrows going both ways, this would indicate an equilibrium exists. That is, you will have a collection of reactants and products in the same reaction environment. So this says you're going to retain a certain amount here and a certain amount here, and those rules will evolve at the appropriate time in the future. Now, when we write a chemical equation, it must conform to the law of conservation of mass as well as the law of conservation of charge. Now, most of you have heard of the law of conservation of matter and energy, but some have not heard of conservation of charge. You must have an issue of charge balance within an equation. So rules for chemical equations and at the same context, reactions must conform to one law of conservation of matter, weight, law, conservation of charge. Now, energy is neither created nor destroyed, but we'll find out how that energy balance fits into the equation when we get to thermochemistry and how it is endothermic, exothermic, how the sides balance and so forth like this. Law of conservation of mass can be also translated into what we call the law of mass balance, which simply means, and most of you already know this, the sum of all the masses of the reactants must equal the mass of the products. Now, in the context or concept of law of conservation of charge, this refers primarily to what we call oxidation reduction. And an oxidation reduction reaction is characterized by change in oxidation state. That's by essential definition, and it's redox by abbreviation is defined as a reaction that undergoes, whose elements, I might say, simply undergoes changes and oxidation state. part of the reaction we call a half reaction. You'll learn about that before we get out of this section. Half reaction can be defined as an oxidation reaction. And by definition, those are reactions which lose electrons, by definitions. Reduction reactions are those half reactions that gain electrons. Now, it is a kind of a semantic issue here when we say lose electrons. Well, you don't really lose them, and they're transferred from one element into the next. And when I talk about law of mass balance, the number of electrons lost must equal the number of electrons gained in the reduction process. Right now, all you need to be aware of is the sum of all the charges in the oxidation process must equal sum of all the charges in the reduction process. Number of electrons lost by certain elements must equal, you have those over there that will gain them in the context of reduction. So when we talk about chemical equations and chemical reactions and things, they must conform to these two laws. One, mass balance, which we'll focus on up front when we start working on some of the balancing. And second, the concept of charge balance, in which oxidation reduction plays into the issue, where elements that lose electrons have elements on the other side of the fence, so to speak, that gain electrons. Okay. So these are just some contextual issues. Now there's one other issue that I say none of you are familiar with. It's called standard state of the equation. Anybody ever heard of standard state of elements? Usually the students are very unfamiliar with it, even though you've played with equations in earlier courses. To start this, I'll give you an example. If we wrote the equation for formation of water, I think everybody would, understand that pretty closely, and I'd say most of you know how to balance it. Number of hydrogens on one side balances the other nitrogen. But let me ask you this: why is hydrogen always listed as an H2? Why is oxygen always listed as an H2? Why didn't we just write this thing, here's an H2O, why don't we just write this 4 H's plus 2 oxygens goes to 2 waters, H2O's like that. Well, why can't we do that? Anybody ever heard of standard state elements? This is incorrect, because hydrogen and oxygen, as a matter of fact, another 6 of them, and some of you know, have to be in diatomic form. Okay, these are called basic elements, in standard state. Basic elements in standard states. Well, what does this mean? The standard state refers to standard thermodynamic conditions. 25 degrees in one atmosphere. That's what we mean by the idea of standard state. When an element is written into a molecular equation, it must be written in context in standard state. When I say molecular equations, that's the molecule. It could be ionic compound or molecular compound, covalent compound, however you want to put it. But when I say molecular equation, this is a molecular equation for formation of water. Okay? So it just shows the whole compounds in the state of existence, like gases, solids, and liquids, and aqueous, and stuff like that. Okay, so when you write into a molecular compound, elements must be entered in the standard state form. So let's say we have hydrogen reacting with chlorine before it enters, and we're going to form a gas, hydrogen chloride. Hydrogen chloride. Well, how do I just put an H and a Cl and HCl? Is that the way I do it? Not exactly. Now, the way you tell what's standard state and what's not standard state is you have to have access to a thermodynamic table like this. Here is an example. Thermodynamic quantities for substances. 25 degrees, and it doesn't give the 1 atmosphere, but all of those tables will be listed at 25 degrees, and that means there's standard thermodynamic conditions. But the issue that you need to pay close attention to, look at the elements that are under this term delta H. See, right here is a delta H. It's got a little F under here and there's a little circle at the top. That means standard heat of formation. The standard heat of formation for any element in standard state, don't consider ions, and electrons and stuff, will be 0. Look at this. So if you wanted to write an equation that included aluminum in solid form, you would have to put Al, solid form, plus whatever it's reacting to. If you wanted to use barium, you would have to use it in this form, BAS, and you look it up in these tables like this. And so every element in standard state is 0. Now here's a very important note. All and only elements, not all elements, but only elements have 0 standard states. Now you have different forms of a given element. If you look at bromine down here, for example, bromine, only 1 is a standard state form. So bromine in gas phase, or bromides in gas phase, or aqueous phase, or bromine, one bromine element in gas phase, and here it is in hydrogen bromide. Well, we'll talk about compounds in a minute. But see, you have multiple forms of the element. Only 1 is standard state. The others have numbers out here, and we'll explain those numbers at the appropriate time. But right now, if you were wanting to decide on what form to put this chlorine, if we come in here and we find chlorines in here, and we see right here chlorine is 0, so I want to put it in that form. And if I'm going to use hydrogen, I need to look in here, except for aqueous H. We're talking about neutral elements, basic elements in their standard form. So I have to put them in whatever this book says they are in molecular form. The ions are not molecular form. So those are called thermodynamic quantity tables. So H2 gas. So that's the delta H F is equal to 0. And it's in kilojoules per mole if you've got to have that. chlorine, you look in there, is Cl2. Okay, it's also a 0 kilojoules per mole. Hydrogen chloride, if you look it up, has a number. Right. Matter of fact, only, now I want to emphasize this, only elements have zeros. Compounds and different forms of the elements have numbers sticking out there in that. If we looked up, let's see, and look at the chlorine and show you. Chlorine gas right here. Okay, see, it has chlorine, hydrogen chloride gas. That's what I'm making. Some byproducts of the reactions are in gaseous form, like HCl. Okay, it has a number out here. Compounds always, and different forms of a given element, even multiple forms. Only one in that set will have a 0. Compounds, ions, anything that's not listed as a standard state element will always have a number out there. Now, use of that number will come in the appropriate time. Okay, so what do you need to know right now? At basic standard state, elements are entered into molecular equations in basic standard states. And to identify that, you go to the thermodynamic table and look up what we call the standard heat of formation. Delta H of 0 always is 0. That's the basic standard state. Now, one other thing that it means is this is the most common form of that element. If you walked out and picked up some chlorine off the sidewalk, it'd be in a Cl2 form. Okay, hydrogen, and anyway, there are, for interest's sake, and some of you already know this, how many diatomics are there? Anybody know? Anybody know? How many diatomic elements are there? Anybody? Nobody know? Oh, okay. If you start with nitrogen and you block out this little collection right here. See going across here? Right down here. What number does that look like?
7.
What number does that look like? Anybody? Come on. 7. Okay. There are 7 diatomics. You just have to remember hydrogen over here, H2, is also a member of that collection. But if you put this set right here into a chemical equation, it goes in as an N2, O2, F2, Cl2, Br2, or iodine 2. Now, acetine is a metalloid and has some weird properties, and they sometimes are by themselves. And so these are the diatomics. Now, I'm not going to go in through all the weird arrangements, but this one is kind of classic in that there are 7 diatomic elements, and you can pick those out if you have a periodic table real quickly in context because it makes a 7. So that's very useful. So in the essence of writing a substance into a chemical equation, elements are always entered in basic standard state. And so now, hopefully, you have a picture of, well, if I have a verbal equation and I need to write in the elements, I'll go to the table and look up that element, and if it has 0 out there, that's the form I use. And of course, compounds, as I indicated, always have a number, and we look up what this is. Of course, the gas phase, and delta H formation does not equal 0. Now that's about all I can give you right now and have anything make sense. Anything that goes beyond that is for another point in time. So in the context of learning about chemical equations, one of the things that students need to understand is, well, what form do I use when I put certain things down? And the elements are the biggest confusion that students run into from time to time. And this. So we had hydrogen plus nitrogen goes to some compound. What the compound is not important. But how do you know what form? You just don't write H and N and then balance the equation. And the context that you have to go to the book, look up what the form of the element are. Now, not all of them obviously are diatomic. Some of them are monatomic in their basic standard state, but you'd look up those, and that's how you would enter these into this equation. And then you would go on to write the formula that is, of course, being formed, and that's another story altogether. Some hydrogen nitrogen combination. There are hundreds of them. Okay. Yeah. Given a compound and need standard state of formation equation. What's the standard state of formation equation mean? If I give you HC2H3O2 aqueous, it's a compound, molecular formula. Compounds that are listed in that table are listed as standard state. A standard state compound like this is written, comes from, or the, I'm having a hard time saying this. Compounds are formed from basic elements in standard state. That's what I want to say. That's a yes and no in the context of what I'm saying. You can make a compound in many, many different reactions, obviously. But if you're given a formula and you need to write what that compound is formed from in terms of elements, you're writing the formation of compound from basic element standard state. Basic elements in standard state. Now, what is this formed from? Hydrogen, carbon, there's some more hydrogen, I'll leave that right there, and oxygen. Yields the HC2H3O2. When we write a formation of a compound from basic elements in standard state, we put the basic elements in standard state. We look up hydrogen, oxygen, carbon. Hydrogen in standard state is H2. We just saw that. Carbon, we look it up, it's a solid and it's graphite. You can look it up in any text if you get it. And oxygen's O2 gas. So this, and this goes to HC2H3O2. So we have 2 carbons and 4 hydrogens and the 2 oxygens. That's a formation of a compound from basic element standard state. Now here comes something very new to you. I dare say anybody in here haven't very much experience in this. Now, a moment ago I said, what is the delta HF of basic elements in their standard state? And I don't know why this thing needs this. There. Okay, here we have delta HF is what I've got here. This is 0. This is 0, and this is 0. All of them are basic standard state elements. That's just what I told you. But for acetic acid, the basic standard heat of formation is a minus 486 kilojoules per mole. You need to learn this right now. That when elements come together to form a compound, they give up energy. If hydrogen reacts with hydrogen, they give hydrogen bonded to hydrogen. That's a chemical bond, 2 electrons. Formation of all chemical bonds. Energy is always liberated when 2 elements hook together. Amount varies for the different kinds of elements. If it didn't give up that energy didn't come out, bond would not form. Now if you want to break that bond and you have so much energy out, you want to break that bond, you put in the same amount of energy, break the bond. Okay? So when we look at acetic acid up here at a minus 486 kilojoules, and that's the way it's designated in our heat and thermo. Kilojoules are calories, and the table's in kilojoules. In the formation of this compound, from basic elements in standard state, 486 kilojoules is given up when all the bonds are formed, making that compound, because we start at 0 on all these. And they go through the process of making compounds. They break and then they realign and do whatever they do. But acetic acid is this. And every one of these, and double bond, this bond, and these carbon-hydrogen bonds, all give up a certain amount of energy. And you add up all those individual energies, and we'll do that when we get to chemical bonding. Add them all up, they'll come up to 486. Because it is a standard operating procedure when you talk about these delta HF in a chemical equation, the heat of formation of a compound in a chemical equation. That number that you have for the compound is from basic elements in standard state. Now that may be kind of new. It's not complicated. You just remember that you look up the elements that make up the compound. This is a number you look up. There's no calculation here. This is a number, standard number. It's in every book that you buy, chemistry book. The delta HF number for acetic acid in this book and any book you go buy or look them up online, it's going to be 486 kilojoules per mole. And you look up the standard heat of formation for any basic element standard state, it's going to be 0. And if you go from reactants to products, it's going to give up 486 kilojoules. Here are your H2 at 0, carbon at 0, and oxygen at 0, your 2 hydrogens right there. All those are at 0. But here, HC2H3O2 is down here somewhere at minus 486 kilojoules energy liberated. Now, that's kind of straightforward. And it's very important that you understand when we talk about chemical equations, they're talking about going from one set of bond structures to something on the product side with a different set of bond structures, and in transitioning that, energy is gained and liberated and lost and gained all the way through. A lot of things are changing, not just a bunch of letters and symbols. But the real chemistry of this is found in, well, you break this bond and this bond forms, gives up energy, and if I want to break it back, I put that much energy back in and go back the other way. So the idea here is not just to get you writing A plus B goes to AB, is to understand that when you write out a chemical reaction, there are things going on in there that you need to be tuned into and understand. Like energy is gained and lost in the process of chemical change. Like that. We talked about structure of chemical equations, reactant products. That's all you need to really have to worry about. Writing chemical equations, elements, and compounds in basic standard states is look up and see what delta HF is in the book. Now listen to me carefully if you miss this. Elements have basic standard state, and so do compounds have a basic standard state. Both of them. Only elements have zeros, and compounds always have a number or various forms of the given element. Okay? And then for any chemical process, we'll have a change in energy occurring. Okay, so when we talk about chemical equations and chemical reactions, things of that nature, these three things have to be kept in the back of your mind. And we talked, of course, the structure and the law of mass balance, and we're going to get in more in just a second, and so forth, like that. So this is kind of a thumbnail introduction to some of the rules and regulations that we need to keep in the back of our mind. We don't always quote them, but we need to understand that they exist when we deal with writing out this weird-looking chemical equation. And chemical equations and formulas can be in various forms. Okay, that's our next topic, forms of chemical equations. Now, we've already mentioned one, molecular equations. This is when the compounds are written in terms of their chemical formulas. Okay, so we got hydrochloric acid and sodium hydroxide reacting here to form sodium chloride and water. That's what we want to write. We want to write this in an equation form. So hydrochloric acid, and we look in the book, and we look up hydrochloric acid in the textbook under delta HF, and we see that hydrochloric acid in solution is written like this. AQ means aqueous, G means gaseous, L means liquid form, S solid, that kind of thing. Sodium hydroxide, NaOH, is also an aqueous. Okay, so we look in the book and we find sodium hydroxide. It's going to yield sodium chloride, like that, and that's aqueous. And water, and we know from experience that water is in liquid form, like that. So we've translated the names into equations, and this is called a molecular equation. Now, there are things called ionic equations. Ionic compounds are named ionic compounds because they ionize. If you have an ionizable compound, you write it in ionic form. If you don't write it in ionic form. You can't write it in ionic form. Let me put it that way. You shouldn't write it. Acids and bases in this context are ionic substances, ionic compounds. Sodium chloride is an ionic compound. Sodium on the left and chlorine on the right side of the periodic table. Here, those are ionic. But water is not an ionic compound. Now, it has a ionizable contact, which we'll learn about when we get way over into Chem 2. but not here. For right now, that's a molecular compound, and molecular compounds, 2 or more nonmetals, don't ionize. Something from the left, metal plus nonmetal ionic compounds, they will break down. Now, how does this break down? Well, it breaks down at the cation and the anion, right through here, and the metal and nonmetal, just like you should know by now. Okay. So if I write the ionization of this, I'm going to write H plus and aqueous for each substance that comes out of that compound. That's the ionic form. And then I go through and here Na plus aqueous plus OH minus aqueous goes to sodium. Will come down here. Sodium plus aqueous plus chloride aqueous. But water is not written in ionic form. If it doesn't ionize, you don't ionize, write it ion. But this is what we call the complete ionic equation. It shows all ions involved in the reactive process. Cations, anions, and then the formation. This is, in essence, you'll see this in the near future, called a driving force. It's always found on the product side. It's a substance which, when formed, hooks together. Okay, doesn't come back apart and prevents the reaction from going backwards. It keeps it from going backwards. And so it always, it's kind of like tug of war. This pulls the reaction to completion on the product side, like that. Now there's one other form that you need to be aware of, and that is the net ionic equation. The net ionic equation shows only those species in solution or in reaction that actually form the compounds. They show only those substances which will undergo reaction. If you look at this composite ionic equation, you'll see that you have elements on the reactant side that match elements on the product side. These are called spectator ions. They do not enter into the reaction, and you can kind of cancel them out like you would cancel out in an algebraic equation. The resulting, or whatever's left, is called the net ionic equation. So we have hydrogen, hydroxide makes water. Hydrogen ion connects with an hydroxide ion and gives you H. And I'm going to put it like this for just, of course, that's H2O. Shows you that the hydrogen hooks up with the OH and makes water. And of course, that's liquid. So when we talk about forms of a given equation, this is one set. Now there are some other forms. Half reactions. Half reactions are primarily from oxidation reduction processes. And let's see if I can find a few here. This little table right here kind of give you an idea. These are standard electrode potential table. That's for the numbers over here. But here, when you look at this, it's a bunch of little reactions which show the electrons involved in here. Now, the electrons in here are all, in all of these cases, on the left side of the arrows, right there. means that whatever you're talking about right here is gaining electrons. If the electrons are on the right side, see over here on this table on the wall, I've got a table of what they call oxidation potentials. And all the electrons are on the right side of the equal sign. Okay? And so that means those are giving off electrons from whatever's on the other side of the equation. But all of these are called half-life. Now if you want, let's see, I'll just take one here. K plus an electron goes to neutralizes to K neutral and is a solid. Okay, that's what it says right here. Okay. Now this will combine with something like let me find a 1-to-1 ratio. Let's see. I don't see anything else. Sorry, I don't see another one, but I'll just pick one nickel. Below that, there is, say, a cadmium plus two electrons, and that produces cadmium, like that, right out of this table. You know, I just looked it up in the table right there. No big deal. This one, this cadmium reaction is below the potassium reaction. That means it delivers electrons in that direction. Electrons are lost from up here, and they're gained down here. Well, on the lower end of this, again down here. If you want to write the proper forms of these two equations, the one that is losing electrons, like I explained over here a moment ago, has to be written with the electron on the right side of the equation. Well, here's it's on the left. So what you have to do is you have to reverse and you wind up with K metal goes to K plus an electron. That's oxidation. Half reaction. So what I'm trying to teach you is this is another form of writing chemical equations, chemical reactions. It's a half reaction and it indicates that that substance is giving off electrons. Whereas then we look back up here at this cadmium, and I want to show that as a reduction half reaction, so I'll leave it as is. I'll write cadmium plus 2 plus a couple of electrons goes to cadmium as a solid. This is a reduction form. Now this is a good place, and I always do this like this, to show you what I mean by mass balance. Charge balance. If you add these two together, you want the oxidation number of electrons, listen, that's here, to match or equal the number of reduction. Here we have 1, here is 2. So this combination wouldn't work. You couldn't cancel both sides here against the arrows, see? So I have to, and you're given the privilege to double this. That's what actually happens. God made it like that. We can't change it. So here we have potassium undergoing oxidation, and to react with cadmium, we've got to have 2 potassiums. Now I can cancel that and add these 2 equations together. 2 potassiums plus a cadmium ion plus 2 goes to 2 potassium pluses plus cadmium solid. That's an oxidation reduction reaction by adding half reactions together. And I had to have a charge balance. That is, sum of all your electrons in reduction must equal sum of all your electrons in oxidation. And that's what I did. Now if you pull a half reaction out of the book, which I did, now we'll learn more about how to deal with oxidation reduction reactions in more complex forms way down in second semester somewhere. But anyway, you can go in here and pull any two reactions off of this table. Write them down. The one at the top has to be reversed. Anything at the top has to be reversed, and you can add it to any reaction below it. I can put, see, I pulled potassium and cadmium somewhere down here. There it is. So this one is always delivering electrons down. Any up here at the top is delivering electrons down. I can take one of these complicated, weird-looking things down here and react it with something up here. And when I put them together, I have to multiply one of them, maybe, if the charge gains or losses are not equal, and make the E's equal. And then I can cancel them out, and I add what's left, and I have an oxidation reduction equation, a balanced one. And so anything up here can send electrons down here. These have to be reversed. This has to stay as is. You balance the charges, add them together, and you have a balanced mass balance and charge balance in the chemical process.